So in this class, I will explain about the concept of centroid. So centroid actually refers to plane figures which has got some areas. It is the point where the area of a plane figure is assumed to be concentrated. It is similar to center of gravity, where the center of gravity is a point where the weight of an object is assumed to be acting. So here, whenever you have some plane area like a triangle, rectangle, trapezium like that, you can always locate a point in that area, so that the entire area of that plane figure is assumed to be concentrated at that particular point. So here, I will take an area like this. It is a planar area A, whose centroid lies at some point here. The meaning of that is the entire area is assumed to be concentrated at this point G. And if you look at the coordinates of that point with respect to some two reference axes, x axis and y axis, then the reference axis, distance of that G from the y axis is taken as x bar, and the distance of G from x axis is taken as y bar. Because it is vertical distance, y bar is vertical distance, it is y bar, x bar is horizontal distance, x bar. Now, in this class, we will see how the centroid of a planar figure can be computed. So, the procedure of locating the centroid of a simple plane figure is called as the first principles method. So, location of centroid by first principles method. So according to that method, the expression for x bar and y bar is taken like this. X bar is integral x dA divided by integral dA. So this integral dA is nothing but a itself. So therefore you can write it as integral x dA divided by a, where a is the total area. Similarly, y bar is given by integral yda divided by integral dA, or integral yda by dA. Here these two terms, integral xdA and integral yda, you have to understand about that. So integral xdA, it is called as the moment of area dA. Moment of area dA. What we can do here is, I will take a small area dA out of this total area A. So this elementary area dA. Let us take this distance from the y-axis as x. Now, if you calculate the moment of this area about this y-axis, it is nothing but area multiplied by the distance. That means area is dA multiplied by the distance x. So this is the moment of area dA. X into dA is the moment of the area dA with respect to or about y-axis. Similarly, I can write yda as, if I take this distance of this dA, elementary we have from x-axis as y. So yda is nothing but moment of area dA about x-axis, because the distance is measured from x-axis. So this is how the definition of moment of area is done. Now once you integrate this, you are going to get the moment of total area. That is, total area is taken as A about y-axis. And similarly, integral of yda is nothing but moment of area A about x-axis. So that's how the difference. If you integrate the elementary area, then you are going to get the total area. So this is how you can find out, or you can locate the coordinates of the centroid of any simple section. Now let us adopt this for a triangular lamina. That planar figure is also called as lamina, triangular lamina. So locate the centroid of a triangular lamina with base B and height or altitude of the triangle and let it as h. So let us see how we can derive the expression or how we can obtain the expression for the centroid, location of centroid in the case of a triangle lamina. So normally what we do is we take any triangle with base B and height h. It can be any triangle, any type of triangle. It can be acute angle triangle, obtuse angle triangle, or it can be rectangle triangle. So this is how we can write. Now to locate the centroid of this one, let us find out only y bar. So y bar means distance of centroid G from x-axis, that is y bar. You can see here, distance of centroid G from x-axis is y bar. Now what I do is I will consider the base of the triangle itself as x-axis. I am not worried about y-axis here because only I need only y bar. So for the derivation purpose, what we have to do is I have to take an elemental strip like this, at a distance y measured from x-axis, and this width of the strip, let me take it as B1. You can see here in the case of a triangle, width varies. At the base it is B, at the height, at the vertex it is 0. So width varies. Now I will take this as ABC is the triangle and DE is the strip. So the area of the strip is dA. And the thickness of the strip, I will take this as dy because the elemental strip thickness is very small. That's why I have taken it as dy. Now from the diagram you can see here dA can be written as b1 into dy. So b1 into dy is we can treat this as a rectangle. So area dA can be written as b1 into dy. Now we have to use the similar triangle principle. So similar triangles means you can see here CAB and CDE, they are similar triangles. CAB and CDE, these two are similar triangles. So by the property of similar triangles, you can say that the respective sides are proportional to each other. So here, since this is y I have taken, this distance becomes h minus 1 because the total altitude is h. So this becomes h minus 1. Now you can see here the altitude in the triangle CDE is h minus y and the altitude in the triangle CAB is h. So those two you can take the ratio. So that means h minus y divided by h is equal to, you take another set of corresponding sides. So the width here is b1 and the width here is b. So this should be equal to b1 divided by b. So this is the property of similar triangles. The respective sides are proportional to each other. I have taken altitude of this triangle and altitude of the bigger triangle ratio and the width of this triangle and the width of this triangle ratio. So they should be equal. Now from this, according to this, b1 will be b into h minus y by h. This is what you are going to get. So this is the relationship between the variable width b1 and the fixed width b in terms of h and y. Now what I do here is I will take this dA as, now dA you know it is b1 into dy. So b1 is nothing but b into h minus y by h into dy. So this is what we are going to get. Here please note that b and h are constants, y is a variable. Y can vary from 0 to h. So y can vary from 0 to h. So 0 at the x-axis and h at the vertex c. So maximum value of y is h. So now what I will use this definition now. From the definition of centroid, y bar is equal to integral y dA divided by integral dA. Now let us see what is this. So integral dA is nothing but A itself. In the case of a triangle, you know that area of the triangle is given by half into base into height, half BH. Now coming to this integral YdA, so integral YdA will be, now dA is this, so what I can write here is integral, y can vary from 0 to h, definite integral, so y into dA is this, b into b by h into h minus y dy. Just I have substituted for b1. Now here you can take this b by h outside because it is constant. B by h into 0 to h, integral 0 to h, y into h minus y dy. Now we have to integrate this. So if you integrate this, you get b by h into integral of this is hy minus y square. Just I have separated the terms between the limit 0 to h. Now if you integrate that, b by h into first integral is h into y integration is h into y square by 2, integration of y is y square by 2, minus integration of y square is y cube by 3, and the upper and lower limit is 0 to 0 and h. Now if you substitute the upper limit, so y is equal to h is the upper limit, y is equal to 0 is the lower limit. So second that is lower limit will vanish. So b by h into h into h square, y is equal to h is the upper limit, h into h square is h cube by 2 minus h cube by 3. So if you take LCM, 2 and 3, LCM is 6, so you get 3h cube minus 2h cube, that is h cube by 6 you are going to get. So b by h into h cube by 6, or you can write it as bh square by 6. So therefore the numerator integral YdA, so this expression is bh square by 6. Now I can substitute that here, therefore y bar is, the numerator becomes now bh square by 6 divided by denominator is half bh. Now if you simplify this, so that b will get cancelled, so it becomes now 1 h square by 1 h will get cancelled, so you will be getting h by 3, because with 6 and 2 you cancel, 3 will be there in the denominator of the numerator. So h by 3, that means the centroid lies at a distance of h by 3 from the base in the case of a triangle. So from the vertex it is 2h by 3. So that means it is like this. So if in any triangle, if you take the base as the reference axis, centroid G will lie at a distance of h by 3 from the base or 2h by 3 from the vertex. Something like this. If it is a right angle triangle, this is a special case wherein this right angle triangle, G will be, suppose if this is B, G will be at a distance of B by 3 from this edge and H by 3 from this edge. Or it can be from this vertex, if you take it is 2B by 3. From this vertex, if you take it is 2H by 3. So this is how we can locate the centroid of a triangle. The expression we can derive from first principles. This procedure is known as deriving the expression from first principles. So on similar lines, we can derive the expression for the centroid of a semicircle. So semicircle, we know that the circle, of course, it is symmetric. Therefore, in the case of symmetric sections, we can say that the centroid exactly coincides with the geometric center of the symmetric section. Since a semicircle is not symmetric about both the axes, it is symmetrical about only one axis. Therefore, we have to locate the centroid of a semicircle. Let us see that. Now, in the case of a semicircular lamina, now let us see how we can locate the centroid of a semicircular lamina. In the case of the semicircular lamina, you can see that it is symmetrical about only one axis. If you choose this as the semicircle, I will take this diametral axis. This is called as the diametral axis AB. The diametral axis itself, I will take it as the x-axis. Now, if I take y-axis here like this, it is passing through the center of the semicircle. So then, what happens? You can observe here, this semicircle is symmetrical about y-axis. The left half of y-axis is the same as right half of y-axis. Now, let me say the radius as r here. R is the radius, and of course d is the diameter, capital D. So you know that capital D is equal to 2 times capital R. Now in this case, according to the property of centroid always lies on the axis of symmetry. That means here y-axis is the axis of symmetry, so definitely it lies along the axis of symmetry G. So only if you find out y bar, that is enough here. Only if you find out y bar, that is enough, because x bar will be 0 here. If the centroid lies on the y-axis, this x bar is 0. So therefore, that is one property. So now, that means always you can say that the centroid always lies on the axis of symmetry. If the figure is symmetrical about both the axes, then definitely centroid will be the geometrical center of the lamina. If it lies on one of the symmetrical axes, then definitely it is symmetrical about one of the axes. Here we can see that the centroid is the semicircle is symmetrical about y-axis. Now, in such a case, in the case of curved boundaries, it is preferable to go for polar coordinates. So instead of going for Cartesian coordinates for the derivation, we will use polar coordinates. You know that polar coordinates means they are r and theta. X and y they are Cartesian coordinates. R and theta are polar coordinates. 2 dimensional cylindrical coordinates are called as polar coordinates. So the relationship between the polar coordinates and Cartesian coordinates are r is equal to square root of x square plus y square, and theta of course tan inverse of y by x. So this is the relation between Cartesian coordinates and polar coordinates, which we have studied in your earlier lower classes. Another time you can write x is r cos theta and y is r sin theta. So this is another relationship. This way also you can express. That means it is something like this. This is x-axis. This is y-axis, this is origin. If you take a point P here, this P can be denoted using both the Cartesian and polar coordinates. If you are using Cartesian coordinates, so x comma y is represented like this. If you are, this is x, this is y. If you are using polar coordinates r and theta, then join this to the origin. So this is r, this distance is r. It is called as the modulus, and theta is this. This is called as amplitude or argument. So that in using complex numbers, we might have studied all this. So this is how we can represent a point in a plane, either by using Cartesian coordinates x and y, or by using the polar coordinates r and theta. So one linear, one angular is polar. Both linear measurements is Cartesian. Now in this case, we will use polar coordinates in case of semicircle. The thing is, these polar coordinates are helpful in solving problems with curved boundaries. In circle, semicircle, quarter circle, they are all curved boundaries. Then you can go for polar coordinates to analyze the problems. Here also, to locate the centroid of semicircle, we will use polar coordinates. Now, in the procedure is, I will take an elemental strip like this. Here, similar to the triangle what I did. There in terms of x and y I took. Here, since it is polar coordinates curved boundary, I will take an elemental area, something like this. dA is the area, and this since it is along the radial direction, dr is the thickness of the strip, and this strip elemental area I will take at a distance r, small r, from the origin O. Okay, so that r is the radial distance of the elemental area dr is the thickness of the elemental area, di is the area, and this is theta, this angle is theta, and this angle I will take it as d theta. So subtended angle I will take it as d theta. So theta is the angle made by the elemental area edge from the x-axis with respect to x-axis in the anti-clockwise direction. D theta is the included angle. So this is the figure for the derivation. Now, as you know, here we need to find only y bar because x bar is 0. It is symmetrical about y axis. Therefore, x bar is 0. Now, the formula to find y bar is from first principles: integral y dA divided by integral dA. This is the formula. Here, please note that y can vary, this r can vary from, this is r, this distance is r, this r can vary from 0 to capital R, you can see here. So r can vary from 0 to capital R. Maximum value of small r is capital R, that is radius of the semicircle. Now here, I know that y is r sin theta. So what I can, let me find out these two separately. Integral dA is, so now I have to write the expression for dA now. dA can be written as a rectangle as usual because it's very small. This curved boundary effect can be neglected. You can assume it as straight edge, and this elemental area can be written as a rectangle. Rectangle means it is nothing but here this is the length, this is the width. So width is dr now. This length is, you know from the property of trigonometry, this length, this is r and this is d theta. This length of the arc is nothing but r into d theta, where theta is in radians, d theta is in radians. So this is the formula you can use directly from trigonometry. So then length of that rectangle portion becomes r d theta, width becomes dr. So therefore integral dA is nothing but r d theta into dr. Okay, that is dA. dA is nothing but r d theta is this into dr. Treating this as a rectangle, and we have to integrate it, of course, to get this dA. So now here we have, there are two variables here. R also varies as well as theta also varies. Therefore, you have to take double integral. Both theta and r, they are variables here. So you need to substitute for both of them. R can vary from 0 to r, whereas theta can vary from, please be careful here, r can vary from 0 to r, theta can vary from 180 degrees, 0 to 180 degrees. So from here to here it can vary. So that means you can write theta can vary from 0 to pi. Pi means 180 degrees. So it can vary from 0 to pi for a semicircle. For a circle it can vary from 0 to 2 pi. For a quarter circle it can vary from 0 to pi by 2. So that's all the difference. So only theta limits will vary, whereas limits of r will remain same, 0 to capital R. So now the thing here is I have to integrate this with respect to both the variables theta and r. So limits of integration will differ. So I can write this as, you can write like this: integral. So theta is equal to 0 to pi. Then integral r is equal to 0 to capital R. So r dr I will write here, d theta I will write here. So this is integration by separation, separating the variables. So I have separated this because this product we can separate. Then you have to integrate it separately and write the answer. So here what I do here is integral 0 to pi is the with respect to d theta will be theta only. Integration of d theta is theta within the limit 0 to pi. Integration of r dr will be r square by 2. And integrating separately. So r square by 2, limits of integration is 0 to capital R. Now we have to simplify this. So the first upper limit minus lower limit will be pi only, pi minus 0 of course, into here it is r square by 2. So that means pi r square by 2 you are going to get. So pi r square by 2 is the actually area of the semicircle. So that's what you get as integral dA is nothing but the total area of the semicircle with which is pi r square by 2 as you know. So area of circle is pi r square, semicircle is pi r square by 2. So this is the denominator you got. So pi r square by 2. Next let us find the value of the numerator. Integral y dA is the numerator. Now let us see what is the expression you are going to get for the numerator. This here also we have to substitute for y as r sin theta. So we are converting the y in terms of r and theta. So r sin theta is y into dA as usual. You are getting dA as r d theta dr. R into d theta into dr. So that is dA. So double integral once again as usual. So here also if you have to integrate this both with respect to theta and r separately, we can separate the expressions and then substitute the respective limits here. So what I do here is integration theta is equal to 0 to pi. That is the limits for theta. So theta terms I will write sin theta into d theta and separate it. Then integral r is equal to 0 to capital R into r square dr. See, this is how we have to integrate. Now integrate them separately and simplify. Integration of sin theta with respect to theta is cos theta, that is minus cos theta. Minus cos theta between the limits 0 to pi, and integration of r square is r cube by 3. R cube by 3 and limits of integration of 0 to capital R. Now you substitute the upper limit and lower limit. Minus cos pi plus cos 0. Okay. So minus cos pi minus half minus cos 0, that becomes plus 1. Into here if you integrate it is r cube by 3 because the lower limit is 0. Now here if you simplify cos pi, the value of cos pi is minus 1. Value of cos pi is minus 1. That means minus of minus 1 you will get, plus cos 0 is 1. So you will get something like this into r cube by 3. So if you simplify this, this is 1 plus 1, 2. 2 by 3 r cube. 2 by 3 r cube. See, this is the numerator. So this is the numerator. So integral y dA is 2 by 3 r cube. Integral dA is pi r square by 2. Therefore, now what I will get for y bar? Y bar we are interested. What is the distance of the centroid of the semicircle from the diagonal axis? So y bar is equal to integral y dA divided by integral dA. So integral y dA is 2 by 3 r cube divided by integral dA is pi r square by 2. Pi r square by 2. Now if you simplify this, so this 2 goes to numerator, so it becomes 4 r cube and r square. One r square will get cancelled, 1 r will remain. This 3 comes to the denominator, 5 already will be there. So 4 r by 3 pi. So this is the expression for the location of centroid from the diagonal axis in the case of a semicircle. So only y bar you need. Okay. Suppose if the semicircle is like this, if it is like this, then this is taken as the y-axis. The x-axis is the symmetrical axis. So if it is rotated by 90 degrees, it becomes like this. Here, in this case, centroid lies here. So radius is r. This radius is r. In this case, this distance, this is the center. This is the diagonal axis. This distance of the centroid from the center O is 4r by 3 pi. That's all. So you are going to get the same thing whether the position is like this or like this. So it lies at a distance of 4r by 3 pi from the diagonal axis or from the point O. So this is how we have to derive the expression or the location for the centroid of a semicircle using polar coordinates, because it is not curved boundary, polar coordinates. The thing is r radius varies from 0 to capital R, whereas the theta value varies from 0 to pi. In the case of a quarter circle, the only figure says this R varies from 0 to capital R only, whereas theta varies from 0 to pi by 2. This is in the case of a quarter circle. Okay, so this is how. Of course, in the case of a circle, of course, it becomes R varies from 0 to R, but theta varies from 0 to 2 pi. Of course, circle is in the case of a circle. What happens? It is symmetrical about both the axes, x and y axis. Therefore, geometrical center of the circle itself is the centroid. So, in the case of a quarter circle, I can show here how the centroid will be. So, in the case of a quarter circle, suppose if the quarter circle is something like this, x axis, y axis, this is the origin. This is the quarter circle with radius once again r. So, this is also r and this is also r. So, in this case, both x bar and y bar, will be equal to 4r by 3 pi and 4r by 3 pi, like this. It means x bar means from here you have to measure 4r by 3 pi. Y bar means from here you have to measure by 4r by 3 pi. So both are equal here. This is x bar and this y bar is x bar and this is g. Okay. So in the case of quarter circle, so what happens? The centroid will be lying here. Of course, this angle becomes 45 degrees. So this is how the centroid in the case of a quarter circle lies. All these are important because by knowing the location of centroid of simple figures, these are all simple figures: circle, semicircle, quarter circle, rectangle, triangle. Actually, in the case of rectangle also, the point of intersection of the diagonals itself, it is the centroid. That is geometrical center of rectangle itself is the centroid of the rectangle lamina. So sometimes we need to find the location of centroids of composite sections, which consists of more than 2 or 3 simple sections. There, these formulas are useful.